I'm going to get started right away because I always have more than I can present. So, yeah, that's me. I was on the faculty in geotechnical engineering from 1964 to 2002. I was chairman of the department from 94 through 2002. And they've allowed me to hang around and keep in office and do all sorts of fun things since I retired. But I have, over a number of years, made this presentation about the Tarbela Dam to slope stability courses and those dealing with dams and levees, because there were so many issues associated with the Tarbela Dam that are rudimentary to dam design and slope stability. So whether Professor Otta or Demetrius teaches the course, I usually make this presentation so that you get a little bit of a feel where some of the basics actually enter into the problem. Now, the Tarbela Dam was a part of the agreement between United Nations, Britain, and India, and on the independence of India in 1947. The World Bank committed to helping Pakistan build a major hydroelectric project, and likewise for India to build one. In India, the dam was called the Mangla Dam, and that was completed before Tarbela. But in the late 1940s, actually works was started in the investigations of the possible location for the Tarbela Dam. So we're going to see that there are issues associated with, first of all, hydrology. Is there going to be enough water to fill a dam, fill a reservoir? Hydraulics, how does the water move? Much geotechnical work. However, this is not a clay core dam. This is a rock fill dam. And we're going to see what that means as the time goes on. So this project was, the rudimentary part of it was started in the late 40s, and then the dam was actually completed in 1976. But there was a lot of stories along the way, so we'll see about some of those. Here is a representation. There is the dam. Here is the service spillway. And this was, in 1976, a cover of ENR. Who knows what ENR is? Some of you. Engineering News Record. It's a construction disciplines magazine. And Tarbela was often covered in their issues. But before I move too far beyond, I'm hoping that most of you have had some exposure to geology, engineering geology in particular. And I can't go beyond this because we see here one of the critical uses of knowledge of geology in the design and construction of this dam. This facility is an irrigation outlet tunnel. But notice the rock formation above it. And I'm going to show you a little clearer picture, and you don't have this in your, there will be a few that you don't have in your slides. Here is that outlet of the irrigation tunnel, and here is the geologic formation. The site for this tunnel and outlet was chosen because of this geologic structure. It's an anticline, and the tunnel then was bored right along the axis of the anticline, and the particularly strong structure. So geology has played a major role in everything associated with dams all over the world, almost every place. Well, of course, here's India, and the separation at the time that the British gave up control was into two Pakistans, West Pakistan and East Pakistan. East Pakistan is now Bangladesh, and we're dealing with the Tarbela project, which is about here in the country of West Pakistan, now just called Pakistan. Now, the river on which the dam is constructed is the Indus River. The Indus River goes into the highest ranges of the Himalayan mountains. The red line is the Indus. Well, there are branches to it, so forth, but that's the main course of the river. It starts in China. It crosses India and comes into Pakistan. Well, look at the height of these mountains, 28,000, 26,000. Well, over here is Mount Everest at 29,000, but it's in the very high mountains. So that the water reaching the dam location is saturated with rock flour from the glaciers in the high mountains. So again, the star is the location of the dam. Islamabad is the capital of Pakistan. Rawalpindi was the major city at the time the dam was built. Islamabad was just being built as the new capital. Okay, so I'm going to give you a grand tour first of the whole project, and I hope from that you'll see then where various elements will fit in. The main dam, of course, is here, and we call it the main dam because there are two small auxiliary dams out here that had to fill in some saddles where the water would have leaked out. But the entire volume of the main dam, the upstream blanket, and the auxiliary dams, 140 million cubic yards. This is still the largest earth and rock fill dam in the world that is designed as a dam. There are larger obstructions which are essentially just tailings dams, the leftover from mining, and they weren't designed as dams. Now, this dam is about 2 miles long and has a maximum height of about 465 feet. The purpose of the dam, sort of fourfold. The first, one might say, would be flood control. A second, irrigation, to provide water year-round for the agriculture and downstream Indus Valley. Third, electric power generation. As the story goes on, we're going to find that electric power generation becomes the key issue because it has provided fairly low-cost power for the development of the country of Pakistan. And the fourth, recreation. And recreation has turned out to be the smallest component, but that's partially because the level of the reservoir goes up and down. The reservoir that this dam impounds contains, or at maximum height, contains 11 million acre feet. What's an acre foot? Hydrology. It's an acre covered by a foot of water. So 42,800 cubic feet of water, multiply that by about 7 and you'll get the gallons. But in any case, 11 million acre feet, huge reservoir. But the key here is that this river produces 10 times that in a year. You know, we have trouble in western United States filling the Glen Canyon Dam reservoir and Hoover Dam or Boulder Dam, whatever you call it. We can't fill them. don't get enough water out of the Rockies. This dam fills 10 times. Now, to supply the irrigation water, there are tunnels over here on the right bank. It's called right bank because you look downstream. That's the right-hand side. 4 tunnels, well, they are key to my story today. We'll talk about those quite a bit. There is the impervious blanket upstream. Why do we have an impervious blanket? What does that do for us hydraulically? We'll talk about that. The spillways. You know, we just had a terrible problem with the spillway at Oroville Dam in California. Well, the spillways are important. With so much volume available to this, in this river, you've got to be able to spill the water if you need to. So there are 2 spillways. The service spillway, which is intended to be the one that is used most of the time, and an auxiliary spillway. The service spillway can handle maximum flow 600,000 cubic feet per second. And the auxiliary spillway, 850,000 cubic feet per second. That's a lot of water. But sometimes they need to spill it because of the snow melt in June in the Himalayan mountains. So these are major features that we're going to be talking about, and here's a nice aerial view, and the dam itself and the spillways, and over here are the tunnel outlets and the power plant, electric power generation. This is the downstream view of the Indus River, and you see we are coming out of the mountains into the flat Indus Valley, which is an important agricultural part of Pakistan. Here is the dam itself, looking from the right bank to the left bank, and we can turn it around and look from the left bank to the right bank. It looks about the same either way, but it is just a big pile of rocks. Well, it's got some silt and gravel in there too, but no clay. So, coming back to geology. I'm sorry that it's a little bit fuzzy on the screen, but the upper diagram shows the dam site to proper scale. And the center left out, haven't worried about the rocks down here because they aren't important to my story. But the site for the dam was chosen partially because of this blue or purple rock here, which is a very resistant, intrusive rock, not a shale or sandstone or limestone that is more easily eroded. It's a good hard rock. And so this was chosen to bore the tunnels that were going to be needed. Of course, they needed to be needed to function during the construction of the dam as well as later in its operation. Now, however, we need to note some very important issues here. The crest of the dam and the upper diagram is this line. The river bed, or the valley at this point, is this line. The bedrock follows from both sides along this line. The depth of material in the riverbed is deeper than the dam is high. And the material filling the valley is all sand, gravel, and cobbles and boulders. Not a lick of clay any place around. Nothing to stop the water. So, in the design of this dam, one had to accommodate the fact that almost as much water is going to go under the dam as you spill out on the spillways. Important fact in the, for the design. Okay, now here is a cross section. I'm sorry again for the fuzziness of the screen, but you don't need to be able to read it very in much detail. Multiple zones in this dam, and the purpose was to try to trap any small particles passing through the dam to help clog it up. Let's make it more like a clay by filling all the pore space with small particles. And so the core of the dam is this yellow-orange zone. And it's made up mainly of silt, sand, gravel. And then the transition zone, this kind of pinkish, gets a little coarser. And finally, we get over to this tan zone, which is sort of the main structural portion of the dam. Here in a little sharper detail is the cross section, and I'm using this as the starting point for seepage issues. In my experience, seepage in your basic soils course is taken maybe 30 minutes on it over the course, maybe not even that much. But it turned out for the design of this dam, it is a critical feature. In any case, again, we see the segments in the dam. And down here is described what they're made up of. B3, the core, impervious blend of gravel, sand, and silt. Well, that's an oxymoron. Impervious gravel? No way. But it's less pervious than the rest. And you'll see the approximate volumes of each of the various zones. Both the upstream and downstream are faced with large, heavy rocks, riprap, to protect against erosion. On the upstream side, waves. On the downstream side, just weather and so forth. But if you add up all of this volume, you come to the 140 million cubic yards. Another interesting thing about this dam, it was constructed, and the only one so far of this size, with conveyors. Portable conveyors. They would dump the fill material in hoppers and then convey it to various parts of the dam. All the material for the dam came from the next valley over, which is the next valley west of the Indus River. Now, some important features here. This blue line, what do you suppose that line is? What do you call that line? It's the top line of a flow net. Nobody remembers phreatic line? Okay, the phreatic line is the boundary between saturated material and unsaturated material. It's the top flow line of a flow net. But you'll notice how crazy it kind of goes, but the reason is it's passing from one kind of material to another. Another feature of flow on this diagram is over at far right side here. Near the downstream toe are relief wells. Relief wells, the phreatic line, all have to do with flow nets. Now, notice here, impervious blanket. It goes 1,737 meters upstream. Why do we want to cover the riverbed with a blanket that far upstream? We want to control the flow net. What is the flow net made up? Well, principally, let's say we're talking about flow lines and equipotential lines. The flow net helps us find what are the uplift pressures under the dam. How do we minimize uplift pressures? Many, many drops in equilibrium. In other words, equal potential lines. So, this cofferdam is way over here someplace. And so we start our flow net at the upstream cofferdam, which is at the far end of the impervious blanket, and we start our flow net and say one flow line comes along like this, goes under the dam. But all in this region of impervious blanket, what do we have? Equal potential line, equal potential line, equal potential line. The more equal potential lines before you get to a critical point, the lesser is going to be the hydraulic pressure. This was the purpose. So we're going to see a little bit more about these two issues as we move along here. Okay, soil filters. Critical in the design of this dam and in some of the failures that have occurred in other dams, the filter effect has not been taken into account, and piping has occurred. That is internal erosion, wearing away of the soil. The filter is designed basically on the basis of, this concept, that large particles can trap within their closed space smaller particles. And the ratio between these particle sizes is about 7 to 1, about, not exactly. So when you design a filter, you design it so that the material to be protected, and in the case of this earth dam, let's say this is a clay, the clay is to be protected against internal erosion flowing out through the toe and creating a void. So we have to satisfy certain conditions. Condition one, the size of the voids in the filter, that's the filter of the big pieces, should be small enough to hold the larger particles of the material to be protected. So in this toe filter, the large particles have to be a certain size to protect the small ones. The second thing is that the filter material must have excuse me, a high enough hydraulic conductivity to pass the water without building up pressure behind it. And that is something else we need to control. Well, who did the basic work on this? Who can guess? Who's the father of soil mechanics? Carl Terzaghi made the first suggestions. The equations were then confirmed and modified slightly by the U.S. Army Corps of Engineers. Anyway, we have the two conditions. To satisfy condition one, the diameter in millimeters of the 15% size in the filter. Well, this is filter material. This is the grain size of the material to be protected. So the 15%, well, here's the percent finer, 15% is here, and this whole range may work for a filter. And you divide that by the 85% diameter of the material to be protected. Here's the material to be protected, 85% up here, and there's the size. So we have the size in millimeters and two possibilities here in the filter sizes. And that ratio must be less than 4, maybe 5, but in this range. And then the second condition, we want the water to be able to flow through the filter, and that says under the D15 of the filter in this range, divided by the D15 of the material to be protected over here, and that should be greater than 4 to 5. There is another condition, and that's listed up here. Here are the three conditions that are generally required by the U.S. Army Corps of Engineers requirements. Here is that same diagram just expanded so that you see and can read the numbers better and make calculations if you want. But this is a specific material. I mean, it was available someplace and they looked at it and said, yeah, it would work as a filter. And this is a specific soil. So you can't just take this and extend it to any project. It's only for a specific one. All right, we come back again and look for the last time at this whole business of the conditions. Here is our simple dam, a clay or silt core, and the seepage going through a tow filter. And why do we put the tow filter in? So that the seepage never gets to the downstream slope. We don't want it to run down the slope and erode it and cut it away, so you cut it off. Well, here is another representation of the filter idea. This is the material to be protected, and here are the larger chunks that are the filter. And the whole idea is that these get clogged up and they can't get out of the filter, but the filter lets the water flow through. Well, this is in this position because you can read the words. Now we flip this around, and this then is the boundary between the filter and the material to be protected. And so here it is in the orientation associated with this. Now, if the dam were zoned with different materials at different places, there would be a angular change in the phreatic line. And we saw that in the Tarbela Dam cross-section. Bounce back to your first soils course. You probably had a concrete dam and you had to draw a flow line or flow net underneath it. And what is the problem? The problem is that the biggest hydraulic gradient is right here. And here is where we need to have that filter so that this material in the permeable foundation doesn't wash out and create a void. Internal erosion is what we want to avoid. So here it is with respect to something you may have seen in a basic course. Now, back again to our main dam and blanket. The main dam is up here, and this olive green or whatever you want to call that color is the upstream blanket covering the riverbed for a quarter of a mile upstream. No, more than a quarter of a mile, they have 1,700 meters. 3/4 of a mile upstream. And this yellow thing is the cofferdam. Well, in cross-section then, if we draw a line through this way, then here is the cofferdam, this little thing up here. Here's the main dam. This whole area was covered with a blanket, which was just made up of sand, silt, clay, boulders, everything that could be collected from around the area. And what was the idea? Here is the cofferdam. That's where our flow net starts. The first flow line comes under here and way over here and maybe out the relief well. But along the way, to all these drops and head, all these equipotential lines. So that is what the purpose of the upstream blanket was, to reduce the uplift pressure on the main dam. Because when you have 465 feet of water on top, that's pretty heavy pressure. And you don't want it lifting up on particles in the dam. Now, what happened? As you'll see in a few moments, there was need at various times to quickly drain the reservoir. And the first time they drained the reservoir, whoa, what did they see? 500 of these sinkholes in the upstream blanket. Well, they weren't unexpected because we knew that the riverbed was very porous and it could easily collapse at various places, but never anybody expected 500 of them. But you can see that even during the partial filling of the reservoir, the silty material formed a cake on the top of the basic riverbed material. And this cake, when it dried out, looked like this. That's a 50 millimeter lens cap there, about 2 inches. And you can see the pattern of the shrinkage of the silt particles, which are essentially rock flour from the glaciers, from the river. And so the intended expectation, I should say the expectation from silting by all this rock flour happened. And it's going to be an advantage because it's going to clog up that blanket and make the flow net work even better. But in the meantime, we've got 500 of these sinkholes. Well, it was thought that they better be filled. So a whole project, several $1 million was required to buy these bottom dump dredging barges. Here we see one that's full and is sitting down low in the water. This one ready to be filled. And then they are taken out in the reservoir, and with precise surveying, geodetic engineering, civil engineering, position the barge and dump. And so they filled up 500 and so of these sinkholes. I think this next slide you don't have in your bunch, but the thing that struck me about it after I put together the slides was, there's the bathtub ring. That's where the reservoir is going to go. And it got there. It got there quite fast. But this is the whole barge operation out there, fixing up those holes. So we come back, make a final look here again at the fact that the phreatic line is a rather tenuous thing going through the zoned dam, and for different elevations of the normal pool, at various elevations here, this looked different. Some places it would look more like a common phreatic line. But the point was, over here we have the filters, and we're draining this into what's the A1, slope protection, that's the riprap. But in the ground there are relief wells, and we expected water to go through the dam and under the dam. We better measure it. How much is going through? So at the toe of the dam is here, and this is the toe, and this is during construction of the toe drain. And various places along the toe drain, like this location, and where we are now, there were weirs. What does a weir do? Hydraulic engineering. You design weirs. Okay, they're to measure flow. They are of a particular shape. This is a tapered channel. And the height of the water, measured by a stick over here, anyway, the height of the water tells you what the quantity flowing in it is. So they were measuring that quantity. And of course, we had relief wells. This is a construction of the toe drain. But here's a relief well in more detail. It's just simple. It's a pipe with a screen on the bottom, and it allows water to flow out to relieve the pressure in the flow net. And then all of this water is collected. It passes by the weirs and here it is being taken away from the toe of the dam and out into the Indus River. And along the way, there are additional measurement weirs to calibrate the amount of water that's flowing and compare that with calculations. All right, now we come to the big event. In the summer of 1974, the dam was quite far along, and it was time for the first filling of the reservoir. But there are some complications here. I'm going to move forward, and then we're going to come back. But here are the 4 tunnels. 2 tunnels, number 1 and number 2, were both destined to go into the power plant. And number 1 is shown here already connecting to the power plant. It wasn't quite there yet in the summer of '74. And the 2 blue tunnels are intended for irrigation outlet. And they were quite closely controlled with gates at this location. Well, it turned out that for Tunnel 2, they had designed into the dam, into that tunnel, the ability to close off the tunnel during certain construction operations. And that was done with an auxiliary gate. This is the entrance, a drawing of the entrance to Tunnel 2, a Morning Glory entrance and a stop block gate. And this gate was intended to be used only once or twice during the correct construction of the dam. A little more detail, it looks nicer over here with the boom for installing this Morning Glory system and the gate, the hemispherical valve here. And here is this temporary gate. The intention was that, oh, they'd just fill this all with concrete when things were going well. Well, the contractor got to the engineer. And by the way, the engineer was from New York, Tibbet Abbott McCarthy Stratton, short TAMS. And they are still in existence, but they were the designers for the dam. Anyway, the contractor got to an engineer there who was in control of the operation of the tunnels. And he says, yeah, you can open and close it one more time. Well, of course, nobody was ever down there to look at the gate or its guides or whatever. And what happened? Well, here I'll just show you a little bit about the gates, the lifting equipment up on top, and the gates way down here at tunnel level. Tunnels 1 and 2 are a little deeper than tunnels 3 and 4, and we saw that back on the geologic diagram if you ever want to look. But these lifting structures are major in themselves. Here on normal horizontal and vertical scale, and here foreshortened. And there is the main gate and an auxiliary gate. Always have a backup when you're talking about structures of this size. And there's the lifting equipment for the gates. Hydraulic lifters to move the gates up far enough so that they clear the tunnel, and the gantry to work on those. And so here is sort of what the situation was on the day the contractor asked if he could use that emergency or that construction gate one more time. Over here, this is tunnel 4, 3, 2 is coming right here, and 1 already going into the power plant. Well, it wasn't on that day, but that's what happened just a few months later. So the contractor started to operate the gate, and he tried to close Tunnel 2 upstream gate. Let's see, I just show you here the downstream stilling basins for tunnels 3 and 4, because we're going to see those in just a minute. All right, so this is what happened. The gate closing, it wouldn't close all the way. They didn't have enough force in the hydraulic system operating that gate to push it farther down. They didn't have enough capacity to pull it up. The gate was stuck. And you've got maybe 200 feet of water above it. Well, that forced water under the gate. Turbulence occurred here. Turbulence destroyed the tunnel in this region, washed out part of the dam up here. Here a little, maybe a little more detail of the gate being stuck in a partially open condition. And I don't know why these arrows are showing upward here, but in any case, major turbulence. Here are tunnel ribs, steel I-beams, bent to the shape of the tunnel. They were just totally destroyed. All of the dam up here was washed away. Just upstream of the junction of where the main tunnel and the downdraft would come, washed out the dam. Here you see the ribs of the tunnel. They don't look like much there. We're going to see them in a minute. And here looking down, after all of the water was drained away, this piece of concrete here is there. What is this? It looks strange, but when you have major flow, you've got to have makeup air or you're going to create a vacuum. So these were the tubes that were bringing makeup air to tunnel, well, 1 and 2, they both had to have it. And eventually these were broken out so that you could get in and work on tunnel 2. Down here you see the ribs. This is what the water looked like coming out of tunnels 1 and 2 during that 1994 summer. Chunks of concrete and rock came out of there the size of a Volkswagen. Just tore things up. Tunnels 3 and 4 were flowing full too. We'll see those in a moment. So downstream, this is what it looked like. Tunnels 1 and 2, 1 and 2. 1 hadn't been diverted to the power plant. You see the power plant's still under construction. 3 and 4. The water just pouring out as fast as they could get rid of it, trying to draw down so that there be no further damage. Well, so this is what Tunnel 2 looked like, and this was the cover of Engineering News Record in the late summer or early fall of 1974. The tunnel, 45 feet in diameter, 2-foot thick walls. You can see steel ribs had just torn out. The turbulence was just enormous. Here you can see ends of these I-beams, which were parts of the ribs of the tunnel. Professor Ritsu's tunneling class. It's a lot of fun. You've got to take that. Anyway, this is reconstruction of the invert of the tunnel 2. Now, the stilling basins of tunnels 3 and 4. The water came out of there horrendous speeds. Let's see. And the basin of the stilling basin was torn up. The concrete, big blocks, eroded concrete. And the dam itself totally eroded away in this region. Here are the air makeups for tunnels 1 and 2. These are the downdraft morning glory inside the gate chamber. The water came through there, it was turbulent, chewed up the concrete on these pillars. See a little bit better, but poorer photographs. Chewed up the concrete, just tore it away. So this is what the water looked like coming out of those tunnels, 1974. This is a different time, but it shows tunnels 3 and 4. They're stilling basins and the Indus River. They were controlled by these gates. During a comparable drawdown to the emergency drawdown, there is a University of Michigan graduate student standing by the flow of water coming out into the stilling basin. This is Barry Bevere. He went over with me 3 summers in a row, and then he stayed on for a couple years and worked for TAMS. You can't tell, of course, because that's a static picture. Water's coming out of there 140 miles an hour. The water coming through those 2 gates is equivalent to the water going by Detroit in the Detroit River. And it was this volume and turbulent water that tore up the basins, the concrete that we just saw. Here is what the water in the stilling basin looks like. What do you call that when fast-moving water hits slower-moving water? Hydraulics, 421. Did you hear of a hydraulic jump? In the lab, you create one maybe a foot high. This hydraulic jump was 100 feet high. It just pounded the floor of that basin and tore up the concrete, lifted out 2-meter thick slabs of concrete, threw them downstream. The floor of the basin was torn up with these big blocks being just thrown out into the river. And it eroded downward from below where the basin floor had been at one time. They eroded deeper down to bedrock in this region, and underneath the peninsula that separated tunnels 3 and 4. All of that had to be refilled, repaired. And here's what the peninsula between looked like, and all the material eroded out. Fortunately, part of it was supported on piles, which remained in place. So repair was implemented, and the basin to the stilling basin was tied down with rock anchors. These anchors went down into bedrock and were pre-tensioned to hold the slabs in place. The next time the reservoir got to a high enough elevation, these were torn out again. Just blasted out like before. So the final solution was to take the stilling basins. Here is a stilling basin, initially down here with a flat floor, and build inside of them a structure that they called a flip bucket. It's just a shaped concrete zone that looks like maybe a ski jump. But the whole idea was to throw the water in the air, get it mixed with a lot of air, and then it falls back into a plunge pool, and you dissipate the energy so it doesn't tear up your concrete. So eventually, stilling basins 3 and 4 were reconstructed. Here's a cross-section up about here, and there's a cross-section maybe there. And the idea was to throw the water in the air, which was finally done and worked. All right, now, still during this process of rapid drawdown due to the inappropriate use of the emergency gate or construction gate, things happened with the spillways. So now we've got to talk about spillways. In this picture, the main dam is over here. This is the service spillway. Auxiliary dam, and this is auxiliary spillway, and more auxiliary dam in these small saddles. Well, of course, when they were trying to draw down as fast as they could, they opened up these spillways. And what happened? Well, let's take a look at them first. Here is the completed emergency spillway, 850,000 cubic feet per second capacity, 9 gates, and you see that they have manicured the riverbed downstream. Oh, nice and smooth, and we'll see what happened to that. And this from the upstream side of the emergency auxiliary spillway, 9 gates. Let's go up closer. Here are the size of these gates. Oh, here he is. There's Barry Bevere with his white hard hat. You can barely see him. Imagine the size of that, and water flowing out of them. Okay, that's what the size of this project was. It was at least 1 order of magnitude larger than anything had previously been built, and so there wasn't experience in this kind of project. So in any case, here's what the service spillway gate work looks like up close, before any water went over it. Here is with the rooster tails, just as it's starting, the first bits of water going over the gate. There's Bevere watching waiting for the gates to be opened. Barry was a great asset to our work over there for probably about 5 years. He went on to be a co-founder of the Delta Group, which is a geotechnical group in Southern California, in San Diego. And they have more recently merged with a larger firm in California. Not thinking of it right now. Now, from downstream, we're looking up at the gates of the service spillway. Before any water had gone over, well, there's some leakage there, but that's not much. And notice again, before it comes the nice manicured zone below the spillway. You can also see some ideas of the layered rock in this region. And all right, so we're going to open the gate, and the water starts to come out, the rooster tails settling down, and the water running down the service spillway. You go around and look at it from the other end. Look at that. A foam spray going in the air 250 feet. What's happening to that nice manicured downstream blanket? Well, there it is again, up a little bit closer. And there's both of the spillways pouring out as fast as they can for drawdown. So here is what the toe of the service spillway looked like after its first drawdown. And initially, if you remember, we had it nice and manicured up to here. That's about a 100-foot drop. And this is a stilling basin. Now, it was intended to work that way. That is a stilling basin because the shape of the spillway was a flip bucket to throw the water in the air again. But it was expected that the the water, after it came down in the plunge pool, would rush out into a side channel of the Indus River. Well, that didn't happen. It just bored a huge hole. There's a reason. Geology. Always come back to geology. Blame it on those guys. But anyway, nobody recognized that there was a fairly large, dark rock dike, intrusive dike, just downstream of this plunge pool. And there is that dark rock. And you see it over here. Here it's been partially excavated, because we've got to get rid of it. We want this plunge pool to go out into the channel of the river. Nobody recognized this barrier, and you can see the black intrusive rocks here, and the lower flow going out from the plunge pool into the river. Here is the rock being blasted away on this side, and it continues over here. And I'm standing in an adit that is a tunnel, safe and away from the blasting, and you see the blast going on over here, cutting out all this rock to open up that spillway. Well, there is the auxiliary spillway and the manicured plunge pool down below. You see, it doesn't quite have the same, I don't know if I have any closer than flip bucket. It's just coming off more or less straight, but here's what happened to that manicured downstream plunge pool. After the first drawdown, it was all torn up. Well, both plunge pools were reconstructed with rollcrete, and just a dry concrete mix, and it's, well, more or less dry, and it's rolled into a dense condition. And so the plunge pools for both the service spillway and here the emergency auxiliary spillway were filled up with that material and solved that problem at a cost of $50 million. Oh, by the way, the total cost of the project by 1976 was $1 billion. Now, next week I'm going to talk about Panama Canal, and it was finished last year. The new locks and reconstruction, $5 billion. Big projects. Anyway, here we see nicely the reservoir and the two spillways. All right, now, who was Casa Grande? Anybody know liquid limits? That little thing you turn. You plot the information, liquid limit, water content, on the diagram. There's a line on that. It's the A line. What is Casa Grande's first name? Arthur. So that's the Arthur Casa Grande line that distinguishes between plastic and non-plastic fines. In any case, he was a student of Terzaghi in Austria. He came to teach in the United States at Harvard University. You may have heard of our professor Richard. Richard first went to teach soil dynamics at Harvard when Casa Grande was there, as a matter of fact. But this was my chance as a young engineer to work with Casa Grande. And it came about again because of sinkholes. Well, one sinkhole in particular. You see this, this is a crane, and this is a roadway built to get down to it. There was one sinkhole in the upstream blanket, not a blanket, upstream slope of the dam. And there was concern over whether the material eroding from that sinkhole did what Casa Grande said it would do. In other words, plug up the interior core of the dam. Well, so I happened to be there at the same time Casa Grande came over to inspect. Here's what the rocks look like, the riprap on the face, upstream face of the dam. And this is where the sinkhole occurred. And that's my left foot. I didn't get it out of the picture. But anyway, that's the big rat hole that Casa Grande came to look at. He was standing beside me at that point, and believe me, I was much thinner at that time. And he says, I wonder how deep that goes. And he says, Woods, you go down in there and find out how deep it is. So, Casa Grande telling me to do this, so I did it. And I only got down about 8 feet. And about that point, I could still sort of reach up and touch the bottom of these riprap pieces. So as far as a person could go is about 8 feet. But they came in and excavated a shaft and followed that sinkhole down to the main embankment materials. And in fact, the silt from the reservoir, from the water that was coming in from the rock flour up in the Himalayas, clogged up the system and stopped the sinkhole. And this was the only sinkhole in the upstream face. No more of them occurred, and everything worked according to Casa Grande's expectations. So here was the excavation, and it stopped at about this elevation. And we just surmised that the water then would carry on down to the main core of the dam, and it got stopped. Nothing else became of that. Okay, finally, seismicity. The dam is located in a region of relatively high seismicity. The Himalayas are always shaking. While I was there, one of the summers I was there was a 5.3 earthquake. 5.3 is not too severe. We all just laughed and watched the ceiling fans do a little bouncing around. Nothing serious, but earthquakes going on all the time. But the question was, in their design of the main dam for resisting earthquakes, the question was, were they able to correctly estimate the first mode, upstream, downstream, natural frequency of this zone dam? Well, at that point in the early 70s, we had Professors Streeter and Wiley in hydraulics here at Michigan, and they were developing a mathematical technique, a finite difference approach, called the method of characteristics. And so they used the method of characteristics to predict what the first mode natural frequency was going to be. They had to have some soil properties, shear modulus in particular, and although I don't have time to show you that, we measure shear wave velocity with a refraction technique at that time. SASW didn't exist yet, and so we were using simple geophysical techniques. So, in any case, checking out the simplest calculations. This is what the inside of Tunnel 2 looked like. Tunnel 1 looked like that as well when they were all ready and finished. So, along the crown of the tunnel, we installed accelerometers. Here is an accelerometer and a control box. Many accelerometers coming into this box. Streeter predicted that when the water flowed through these tunnels, they would create an organ pipe effect. Now, the frequencies, of course, were not in the audio range. It's not an organ pipe that you can hear, but the frequency would depend upon how high was the water in the reservoir, how open were the gates, and so forth. So Streeter was able to predict what the frequencies would be for certain reservoir conditions. And he predicted that you could generate frequencies from about 0.9 to 1 hertz, 0.9 to 1 cycle per second, by adjusting the height of the reservoir. Well, you don't adjust it, you let it go down. It naturally fills up and you let it go down. But in any case, changing the height of the reservoir. So then the question is, if we can generate that frequency range using a tunnel, can we shake the whole dam? Okay, let's try it. So we put our geophones, these are velocity sensors, seismometers they might be called, and they have a natural frequency of 0.5 hertz, 0.5 hertz. So they were good enough to be able to pick up 0.9 hertz. And we established these sensors at the crest of the dam and at the toe of the dam, top and toe, at the 2/3 points along the dam, at 1/3 and 2/3 of the distance across the dam. So we had 2 measurement locations. Here's our student Barry Bevere making readings with the instrumentation. And it's interesting, the gentleman in the white here is Paul Chow. Paul was hired at TAMS in about 1950. Paul retired from TAMS in 95. He worked on Tarbela his entire career. Now, there were some gaps where he worked on other projects as well, but this project was his entire life in hydraulics. Okay, so here is a cartoon of the dam, the crest motion, the C, the toe motion, the T, and so we had sensors up here and down here, not there underwater. And we made the measurements and calculated the magnification. So, in fact, at different reservoir elevations, as we see over here, the frequency of the organ pipe effect in tunnel 2 ranged from 0.9 to 1 hertz. And the solid dots are measurements at the crest, and this is at the 1/3 point, and this is at the 2/3 point across the dam. Crest, toe, crest, toe. And then we hit the frequency of about 0.95 hertz. And we got a jump, and that stayed fairly constant for as high as the reservoir went. So we were able to confirm the frequency of the organ pipe with the accelerometers. We could get the frequency of the dam shaking from our geophones. We got the amplitudes, and we were able to demonstrate a magnification of 4. The crest of the dam moved 4 times as much as the toe. And of course, that's with relatively small excitation, not an earthquake. This was with just an artificial excitation. But it did confirm the calculation method, the method of characteristics, and helped to generate confidence in what had been calculated. Well, we'll kind of wrap it up here now. The representation of the reservoir, only about halfway up the dam, and I can't tell whether it's filling or being drained. But on that same reservoir, at that time, there were still people carrying water away from the reservoir in the goat skins being carried by the burro. And water was being pumped from wells with this kind of a pumping arrangement. You see the long bar, bullocks, one bullock here and one bullock here, and they would go round and round and turn this thing, and it turned this wheel, and the water was pulled up with clay pots. 1976. Here's the wooden, I mean, amazing wood technology here. And in the evening, you'd see the camel caravans come into the villages. They had to go off to collect firewood. Firewood was critical, and camel caravans would bring it into the villages. Well, things have changed immensely in 60 years since Tarbela was constructed. All 4 tunnels are directed towards electricity generation now. A new tunnel had to be built on the left bank for irrigation releases. The reservoir is about 3/4 silted full. It still works fine for electric production because you have the drop in head, but it no longer functions very well for flood control. It does help a little bit for irrigation water. So what were the main purposes? Flood control, that's pretty much gone. Irrigation is getting better, and it's getting better simply because new generations of farmers are willing to accept that they can grow more than 1 crop a year. Their grandfathers had grown up in the Indus Valley where they could only do 1 crop a year because that's when the water came. June, they could do their planting and they could have enough water. It has taken 3 or 4 generations to get into the mode of multiple crop generation, and that's working now. Electric power, it's just been enormous boon to Pakistan. Recreation, not very much. Now, I've got a couple more minutes, and these are not in your pack, but these are scenes of areas that were flooded by the reservoir. About 70,000 people were displaced. There were many university studies going on about the displacement of these people, and I suspect that that has followed on up to this day. I'm not in the humanities area, I don't know what they concluded, but this is what they were flooding out. This is just another recollection of how important geology is, and that tunnel on the left bank that had to be built for irrigation when they put everything else in the electric power, and the anticline. This showed up just after a rainstorm, and the water highlighted the colors in the layers in the anticline. This is what the at an intermediate stage, probably in the 1980s, when water was going out of the tunnels, tunnel 4, and flipped into the air with a flip bucket and into the plunge pool. But you'll notice how long the power plant has grown now, because tunnels 1 and 2 are both being fed through the turbines, and they're making electricity. At this stage, and I don't have a current stage, even tunnels 3 and 4 are diverted to power. Just another view of how huge the power plant has grown. We saw it when it was back here, and now it's all the way out. I was there. That's me. We were making measurements of the lifting structures for the gates in the tunnels 3 and 4. And we lived pretty well. The guest house On the left is the living room, on the right's my dining room, and I was the only one in there. But of course, I had a cook and I had a sweeper. You had to have jobs and people to fill the jobs. That may be the end. Well, yeah, there's the end. So Tarbela is history now, but and there are probably 3 or 4 more stories I could relate about technical issues that we don't have time for. But it's a great demonstration of how many things can go wrong, how moving into the next order of magnitude can cause problems, how a simple thing like, well, this gate has worked up and down before, it's going to do it at least one more time, and we create $100 million worth of problems. Hope that I haven't bored you too bad, and I don't know whether Professor Zeckels will give you questions on your final exam. I hope not. Okay, thank you.